Today's the
Four.
today's the
Yeah.
Yeah.
Not advanced.
Oh, this week. The 14th.
check. Do I have a homework? Should I have a homework 8? Or you? No, okay. I think this is just homework 8. Okay, get started. Well, today is review day, so we can go over problems from the exam, some of those practice problems, discuss some elaborations of those, just answer questions, just by general things. You do get 1 page of notes. You can write on both sides, standard 8.5 by 11 sheet. You can write down formulas, you can write down descriptions of algorithms like Bootstrap, you can write down numerical examples, sentences that might be useful. So whatever you, in your study, want to put down there, you can put down there both sides. Have a calculator for some calculations. Pen or pencil is fine. And we're looking at homework 6 through 8. Homework 5 was on Fisher information. It was kind of on an elaboration of likelihood things that we're going to come back to. But so really the 6 through 8. Monday we discussed some topics that are on there, so that's the guide I'll look at. Nothing on likelihood ratio test. We'll revisit that on Friday after the exam and see a little bit more how that goes. But, those are the topics. But any questions to start out with?
You should also bring the.
Oh, the T table, I can copy that and just kind of include it with the page. So you don't need to bring an extra copy. It's just, I could ask you to bring it, but it sometimes gets confusing. Somebody forgets. So I'll just include that with that. And that's right, we will be utilizing this T table to do things. Right? To calculate T values or Z values for confidence intervals or reference points for hypothesis tests. Right? So the way this table goes is there's degrees of freedom for a T procedure. At the very end, at the infinity, this is equivalent to the normal. And so these are the different percentiles, like 0.975 percentile is used for a two-sided 95% confidence interval. And so at the bottom of that is 1.96 for the normal. But if you have one sample, say 41 sample size, degrees of freedom would be 40, and you'd use 2.02 for on there. Or if you were doing a hypothesis test, I calculated a T statistic, and I wanted to do a 0.05 level test, two-sided test. The reference with 40 degrees of freedom was to be 2.02. So if you're bigger than 2.02 or less than negative 2.02, if the statistic ends up negative, then you would reject. Right? And you can vary the level of, so 95%, 90%, 80%. This one gives you 99% interval, and so you can look up a few of those things. So mostly you just need a few of these columns, and then degrees of freedom for a particular problem. Yep, so that'll be included as part of that. So let's look at some of the problems that are on there. So let's see, where is that then? So this one has.
It's the Word document. The Word document.
This Word document. Oh, those are the problems. So the first one, random sample, 120 individuals in labor force, 80 is not. The average retail sales in the first group is 17,000, whereas 14,000 in the second group. And it says it's bootstrapped 2,000 times, and given this interval, here. And so what is a 95% confidence interval for the difference based on these groups? Right? How would you go about, given that information, what could you do for a confidence interval? So, if this is the histogram of the values, one where we did intervals was just to kind of eyeball it, right? Oops. Kind of take the points on here and say, well, maybe 500 up to about 4,500 would be something like an interval. And so that would be kind of a guide to where it is. If it tells you that the standard deviation of the values that went into this is 824, right? So in number, that's what, number 1. Right? The standard deviation, the standard error, of these is 824, right? From the bootstrap. So if you took the x bar 1 minus x bar 2 plus or minus some t value times the standard error, it should give you a pretty good interval for these things. This was 16,630 minus 13,877, right? Plus or minus some t value, and the standard error is 824. Right? Now, the first group had 120, and the second group had 80. We don't know exactly what assumption they're making. Is it different sample sizes, equal sample sizes? I mean, standard deviations or not? At the upper end, the degrees of freedom, if it was equal sample size, equal variances, sample standard deviations, you do something like this. So you'd use, 120 plus 80 minus 2, so 198 as the degrees of freedom. The very conservative thing to do would be to use the smaller 1 minus 1, so 80 minus 1 is 79 degrees of freedom. Right? If we want to do, it says to make a 95%, so we'll look at the 0.975 column on that chart. And if we do that, right, so 0.975, if it was normal, we use 196. If it was 198, we don't exactly have 198 there, but we could probably use 1.98. That's going to be kind of close. If we had it exactly, maybe 1.97 if you chose something like that. If you're being conservative, taking 79, well, and even rounding down, maybe you'd use 2. Right, so it's going to be a little bit off from 1.96, but not too big. So that'd be kind of a couple different approaches to do. Right? So that should be an appropriate adjustment, make the interval a little bit wider so you get better coverage. Not exactly the precise things that you would do in a government report, but enough to express the idea that we're using t. Right? Well, so if you said 2.0 as an approximation, I think I did it a couple ways on the solution. There's some solutions posted. And so this ends up being $795 up to $4,091 for the difference between these couple of groups, or between those in the labor force and those not in the labor force. All right, so let's briefly interpret this interval. Right? What type of statement would you want to make for interpreting a confidence interval?
And it doesn't contain 0?
It doesn't contain 0. That's going to be one important thing, where these two groups do not have the same retail sales amount. But if you wanted to talk more about the interval as a whole, right, you can always begin those statements with we're 95% confident. Right, that the true difference between the two groups, labor force minus not in labor force, is in this interval. You can always start it with that phrase, 95% confident that it's in there. Right? You're not saying the probability is 95% or 95% of the data or something like that. Yeah.
How did you get the 16, 630, and 13, 877?
These things were.
Because in the problem it says 1700 and 1400.
Huh.
Did you subtract the standard error?
Maybe I did. Is that the confidence interval or what? I'm not sure.
I don't think that's subtracting the standard error because it wouldn't be 30.
Yeah.
It's pretty strange. How did I do that?
Because it's yet 1700 and 1400
Huh. Yeah, 1700 and 1400.
in the problem.
I don't know where in the world I got. Goodness, that's weird. I don't know. But yeah, if you read the problem, then the first one was 1700, and the next one is 1400, right? And so that's where you should center it. So these would not be exactly the same. So sorry about that. That was kind of a bizarre thing. I have other versions of problems that I was just reading and not thinking. But yeah, you really want to do 3,000 plus or minus, right? So 3,000, it should really be 3,000 plus or minus. If you double that, 8, 4, 16, so it's 46, 48, adding it, and then 1352 on the lower side, right? Add that. 4, that's a 4.
Plus.
Right. So does that make more sense?
Yeah.
So, I can go back and correct that. Thank you for doing that. It's a kind of a weird thing. And it says, another way of looking at this thing, another way that the problem like this might be presented is I might give you the 2 standard deviations. Right? So I might give you, let's say, let's go one more. Okay? Okay. Is thing moving at all? Okay, let's see. Okay, just slow. So if I told you that the first one is 120 and the second group is 80, and the average for the first group we'll use 1700 here, and the average for the second group is 1400, 17,000 and 14,000, right? And if I told you that the standard deviation for the first one is 5,700, and the standard deviation for the second one is 5,800, right? We could say make a 95% confidence interval or difference in averages. So the other ways you could use the two-sample T formula for getting a difference. And so that one was x bar 1 minus x bar 2 plus or minus a t value and then standard error. And you could do s1 squared over n1 plus s2 squared over n2. And again, the degrees of freedom, if you're not making them equal, it's a little question of what do you use. But let's use a t value about 2.0. Right? So you describe what you used. 1.97 or 1.98 and kind of wrote out a degree of freedom that you would think would be good. That would be fine. So this difference is 3,000 plus or minus 2 and times the square root of 5,700 squared over 120 plus 5,800 squared over 80. That would give, plus or minus here, that would give a 95% confidence interval. Or that. Calculate the standard error, multiply it by 2, subtract it, and add it, and you get that other one. So part C, as stated in the problem, right, says describe a bootstrap T method of making a confidence interval. I think I would ask this primarily, maybe just like a 1-sample one, but a 2-sample one, right, we could also think about that bootstrap T interval. So you prepared for this, think about how you describe a bootstrap T interval, because it was one method of making confidence intervals. So You bootstrap the data. Right. For two samples, two infinite samples, there's kind of two bootstraps. Right. Sample 120 times with replacement. From the labor force group, from their values. And then we sample 80 times with replacement. From the not in labor force group. And so we end up with two different samples. Our t statistic is we take the bootstrap. So this one gives us x bar 1 star. This gives us x bar 2 star. And we subtract the x bar 1 minus x bar 2 from the original sample and divide by standard error. This gives us S1 star. This one gives us S2 star as well. So S1 star squared over N1 plus S2 star squared over N2. And square root of all that. And we're going to get a large number of t values. Do this many times. And we're going to, we get 10,000 of these things. We're going to sort take the 2.5%, 2.5 percentile, and the 97.5 percentile as t values, and put those into the interval, right? So that the interval ends up being our average of these two things minus the t star values, either the 0.975 value or the 0.025 value times this standard error from the original sample. So if you subtract the upper t interval, it gives you a value that's less than the average. And if you subtract the lower one, which is a negative value, you're going to get a positive interval. So it's a different interval. Why might you want to do this? Yeah.
If you don't think the assumptions of the data is normal enough,
Yeah, if the sampling distribution of the data is not quite normal,
or if you don't have enough values.
small sample size, skewness, then this t interval could shift things, primarily in one tail or in one direction or the other. It kind of compensates for the non-normality or the skewness. Any questions about? Right? You might, work on this, add 1 or 2 lines in there to put in a little bit more of what I said verbally. But you can think about that before the exam. And I said back here, we today is Monday, right? So when we talked about topics, that was on Friday, right? So on Friday we discussed some topics. So if you look back at those notes, they have some details. Right? So that's really this first question with a couple of other variations. Right? Good. Any other questions? To get this, to get those, just as a side, to get these values 57, 5800, I said, well, what if the standard error formula, what if they were pooled and you said you had 1 over 120 and 1 over 180, and if that was the 8, is it 874?
It's 824.
824, right? Then you can solve for that S of P ends up being something like that value, whatever it was. Right? S of P ends up being 5709. And so just to kind of make the difference, one is 5700, one is 5800, to kind of make it as an example. So this standard error from the bootstrap kind of implies that they're kind of around this range. In reality, you might have had one, 6,000, another one 5,400. It might have been more different, but that's why I use those values, because it's kind of consistent with the 524, 824. Okay, so next one. All right, so the next one, number 2 says, new random, so there's a random sample of 100 Vermonters age 25 plus with a bachelor's degree or more. They're 72% active in the labor force. A second random sample of 200 Vermonters less than a bachelor's degree. They're 63% active. Previous government report said there were 70 and 69, 65%. Make a 95% confidence. The difference. So for these, there's the Wilson intervals, but that's much more complicated to do. You do the simple versions in this case. Just as an aside, I'm countering a consulting project which is doing some surveys for the Securities Exchange Commission. They did some travel audits of some of their travel budgets, and they sampled 200 individuals, records, and there's about 8 or 9 of them that seem to be an error in some way. So they want confidence intervals for these things. So it's small sample sizes from a finite population. So the standard approach, the normal approximation probably is not good. So we've got to try to figure out what to do. And there's a surprising amount of literature on things that could be done. So anyway, it comes up. So we're going to do the 95% confidence interval here. Right? So number 2. Right, so a 95% confidence interval for the difference of proportions. So we're going to take P1 hat minus P2 hat plus or minus a normal value, and it says 95%. With proportions, we use normal, so that's going to be 1.96. Those differences here. And then standard errors. And sample proportions. And so it's kind of plugging in some numbers. There was 100 in the first group, and its estimate was 0.72. There's 200 in the second group, and its estimate from the description is 0.63. And so if I plug in those numbers, there they are in there, I got negative 0.0205 F2 0.2005. The estimated difference is about 9%. And that's the interval, right? So you might interpret this interval. What is this? What would you say to interpret this interval or explain what these numbers mean?
You're 95% confident the true proportion.
Yeah, we're 95% confident, right? That the actual difference between the bachelor's degree or more versus those with less than a bachelor's degree, what's the difference in their percentages involvement in the labor force? Right? If you did a hypothesis test, are they equal? Right. Right. Are you going to reject 0? No, you're not going to reject 0 because 0 is included in there. Right. So part C is state hypothesis. There's actually a little bit of 2 ways to go with this. Right. One hypothesis would say that they're not equal. One or equal, right? So one hypothesis could be, right, that P1 equals P2, in which case the difference is 0 versus an alternative, P2, so the difference, is not 0. Right? But looking at the statement of the problem, right, our previous government reports say they were 70 and 65%. So maybe that's based on labor force participation, something about official data. Maybe it's based on a census at that time period, not a survey. Right? What other hypotheses might you set up?
That the difference is 5%
You should set up something like the difference is 5%.
versus the difference is not 5%?
Yep. You know, you could set up that P1 minus P2 is 0.05 based on that data. And this is really then saying, you know, have things changed in the last, right? If the economy is changing and things are getting worse for those without the bachelor's degree, if the economy is going tech-wise or something like that, so you need to hire, then that might be. Or if manufacturing is coming back and somehow you don't need a bachelor's degree to qualify for a lot of new jobs, it might be shrinking. So, but anyway, 5% also isn't going to be rejected. You know, it's 100 and 200, not big sample sizes, so they don't reject it. Here is a randomization distribution. So kind of a bootstrap distribution or simulation of sampling distribution. What do you conclude about your hypothesis? You could take either one, however you phrased it.
Don't reject the null.
Yeah. Why would you not reject? Think about phrasing this, because it'd be good to have a sentence kind of in your mind. How do you say you don't reject? Right? Based on a simulation. Right? Well, if it really were 0, right? There's a lot of simulations that are more extreme, kind of about this way. 0 is kind of in the middle. So 0 is not unusual for the sampling distribution. 0.05, 5% is in here, so it's also not unusual. It might even be on the right-hand side a little bit. So you're not going to reject. Right? It's not atypical. So the p-value, the tail area, is not going to be small. Right? But any questions about it?
So in the test, are we going to be interpreting graphs instead of like actual things where it says p-values?
Well, no, you could end up getting both. And I could give you, one problem that has a graph, and you would say something about it. But then, like the confidence interval problems, you could do actual calculations for some intervals. Or in some of these tests, like this one, was an interval here, but it could be done as a hypothesis test. And then you would get a statistic and say, is it extreme or not? And you won't have the exact p-value because you just have the table. But if it's beyond a cutoff value, then you can reject it at a certain level. A little bit of mix. These practice problems together is probably longer than the total exam would be, so a little more to practice than that. So number 3 here, right, there is Minnesota multi-phase personality inventory administered to 31 men who were aviators in World War II and German prisoners of war. Their scores on this section measuring post-traumatic stress disorder had an average of 9 and a standard deviation of 9.32. Form a 95% confidence interval. Will the 95% interval be wider or narrower than your answer in A? And then the distribution is likely skewed, because if they're all positive, to get that standard deviation, you gotta have some outliers, right? What does that have to do? So in this one, what would we want to do? Right? It says 90% interval. And we had 31 individuals. So, and we're dealing with an average 9.00, standard deviation 9.32. So for confidence intervals or tests, we're going to deal with degrees of freedom equals 30 on that. So the what number do we need on this?
1.697.
Yeah, right. So 90% interval, so we would need the 0.95. 90%, 10% left over, so it's our 90%, and there's that half of that 5% there. And then we go down here to 30, 1.967. 697, right. So our t value, 1.697. Right? So our 90% interval, 9 plus or minus 1.697. And then we need s over the square root of n for the standard error, 9.32 over the square root of 31. And I got an interval in there of 6.16 and 11.84 on that scale. Right? Would a 95% interval be wider or narrower?
Wider.
The more confidence, you got to keep making it wider. And as you move out that table toward these higher percentiles to cover more, they get bigger. Right? So instead of
2.042.
yeah, you go 2.04 for 95%, and this 2.75 for 99%. So you get intervals that cover more of the time. You make them wider to increase the chance that they actually work. And if this is strongly skewed to the right, do we have any concerns?
The data isn't normal enough for the central limit theorem.
So if the original data, right? If the original data for PTSD score was something kind of like you know, this with a skew, right? Or you know, if there's really kind of a smaller group and then like a little few, you know, they're really extreme, unfortunately. Then once we take averages of just 31, the sampling distribution might still have a little bit of skew on it, right? So if this is y, and then if we have a distribution of y bar, it's going to be mostly symmetric, but it could be kind of just a little tilted. Right? So intervals that are symmetric like this might not be the best. If you want to make a bootstrap, like a bootstrap t interval for this, right? So how could that help give you a better interval?
You're sampling from the data. So
Sample
that
from
way
the data.
it gives you the t value a bit more. Really represents your
Yep.
shift.
So, all right, so in this one, we use the t plus or minus. Oops, that's not going to help. The t plus or minus, right? So symmetric. It's kind of based on symmetry, right? But if we simulate t distributions by describing that algorithm and getting them, they can be shifted, and then it works out like a pivot to do a little bit better. So the goal is higher coverage. Get closer to our desired 95% over the long run. We could also look at, suppose, you know, you could have another hypothesis test, right? So say these were World War aviators. Oops. There we go, I'll get back on this one. Who, they were World War II aviators who were prisoners of war, right? What if you gave the same test to World War II aviators, or maybe to just prisoners of war who were not aviators? Right? Would they have the same PTSD scores? So let's say you just take the aviators from World War II. Maybe there's a much bigger group that's been studied there, and it's reported that their average for aviators as a whole is 6 on this scale. Are the ones that were prisoners of war, do they experience more or the same levels of PTSD? You might make a case that it's one-sided because you would think they'd have less, but you can do things one-sided or two-sided. Just do them consistently, and that will be fine. Right? So we can set up a null hypothesis that the prisoner of war ones are also 6 versus, they're not equal to 6, and we could test that hypothesis. Right, so we can set up a t statistic. That's x bar minus mu sub 0, s over the square root of n. And so there was 9.9 minus 6, and then s was 9.32 over the square root of 31. And I started R. No, not going anywhere. No. So anyway, if you calculate that, that would give you a t value. So we're going to do t value of 9 minus 6, difference in mean divided by 9.32 divided by square root of 31. And that your calculator would tell you a t value of 1.79. Is that right? So 1.79. And say we want to do an alpha 0.1 level test. We were doing a 90% confidence interval, right? So we might as well do a kind of a 10% level test. Right? We have to decide if this is big enough to reject or not. Right? So degrees of freedom is still going to be n minus 1 or 30. So the t under the 9.95 column is 1.697. And we're bigger. Right? So we would conclude that, so two-sided, this is the two-sided value. That's why it's 0.95 there. So in this case, we would conclude that we can reject the null hypothesis at the 10% level, right? Because our 179 is bigger than the cutoff value. If I asked the hypothesis testing question and you said, I'd rather compute a confidence interval and then compare my confidence interval to this hypothesis value, you could do that too. I mean, you could answer it either way. Sometimes if I ask hypothesis, it might be straightforward to go through that. But if you reform it as a confidence interval, I wouldn't object if you did that and then did an interpretation in terms of the hypothesized value. So the confidence interval before, right, went down to 6.16. So 6 is going to be rejected at the 10% level because it was 90%. One thing I didn't put on the practice problems was a question about power. Right. So let's say we're going to have, x bar is 9, the standard deviation is 9.32. We're going to have 31 people. If we had a null hypothesis unrelated to that other problem where it's 5, I'm doing 5 because that's what I have in my notes. Right. When do we reject? H0 at a 10% level. What type of x bar would lead us to reject? So power, first step is to calculate where we reject, right? And then calculate the probability of that under the alternative. Right? So we would reject if x bar is away from 5, minus, we have 1.967, 9.32 over the square root of 31. Okay. So if x bar is less than this thing, which is 2.16, which of course is the completely opposite way of the data, or x bar is greater than 5 plus that, that number, that's 7.84. So we reject 5 for greater than 7.84. So this gives us our so-called rejection region. Right? What's the probability of that? Well, the first one's really, say, suppose that the alternative really is 9. Right? What's the chance that we're less than that? Right? So what's the probability that x bar is greater than 7.84 if the mean is really 9?
5.
So 9, so under the alternative.
Under the alternative.
Yeah. For power. If what we got from our sample of veterans is really accurate for the average for those prisoners of war, or prisoners of war, well, 7.84 minus 9 divided by the standard error, 31. I'm sorry, I don't know why I put 32. It's just 32's up there, I guess. And so, you could probably put a z there that is greater than that, or a t, depending on that sample. You could do it with either a z or a t, but anyways, the 0.963. You might not be able to calculate this exactly, unless I come up with a number, unless it ends up being something like -2 or 0 or something like that. But this power calculation would be 0.756 or 753 if I used a t distribution. But that said, there's not probably enough detail in the t table to do most of those calculations. What's one thing that would give us more power for detecting a difference?
Sample size.
Yeah, so then more sample size. How does sample size help? This is something that I think it's easy. You can answer with a picture, right? So instead of the two hypotheses essentially saying, here's one and here's the other, and they overlap substantially, if you get bigger N, so if this is here, this is here, I'll try to draw them. If you have big sample sizes, then these two sample curves are well separated. And so if you're really under this curve, you're not going to be close to this one. And the probability that you're up in this region is very high. Right? So anyway, power, shaded in is kind of like this area. If this or this picture, that's kind of the shading for power mostly, and there's a kind of tiny thing over here. It's kind of inconsequential. Right? So it's really this area over here, and this is much more of the area. It's 50% of the area maybe, or 40%, which is bad. And this looks like 90% or more, which would be good. So sometimes you can kind of you can write out an explanation, what affects power, or you can draw a picture, or do part of the calculation, how does it change the rejection region, and that would give some ideas there. We might run out of time to go through great detail on a few of those others, but that kind of highlights a few things there. Some solutions are posted, and I'll double check some of those. Right. Maybe if I tap it first, and then yeah, tap it and it moves. So, random sample of 250 parents with young children, 144 reported they condone spanking as punishment, regular punishment. High, but form a 95% confidence interval. So that's one proportion, a confidence interval. The newspaper reports 60% of parents condone spanking. Is that reasonable? We can do a hypothesis test. You could look at the interval. Does it include 60%? If it includes 60%, then it's not rejected. I think it's not rejected in this case. This one, right? If we wanted to repeat the study and achieve a margin of error plus or minus 3% for 95% confidence interval, how many should we use?
Only the standard deviation.
This one, because it's proportioned,
don't.
it's included in that,
Yeah.
right? So there's two sample size formulas that we've done. We did a more complicated one with power, but I don't plan to put that one on the test. Kind of the simpler sample size, focusing on sample standard error. If you're dealing with a proportion, the sample portion is usually normal value squared, p times 1 minus p over the margin squared. So 1.96 squared, 0.5, 1 minus 0.5 over something like 0.03 squared. And this gives 1,067 or so, or 1,068 if you round up. And if you had a sample proportion of 0.4 or 0.3, you could put that there instead of, 0.5 is the maximum. You could use that. If you're looking at the mean, right, this was the p times 1 minus p over n was the variance for that. If you're looking for a mean, we usually do planning with a normal. You could adjust it upward because if you have end up with kind of a small sample size. But sigma squared would go over here and m squared. Right? So if our sigma was 9.32, approximately like that, and we want a margin, plus or minus, 0.5, half a point on that PTSD scale, you could 1.96 squared, and this would be 9.32 squared, and if it was half a percent, or half a point there. This is going to be somewhere around 100, I don't know exactly. It'd be less than 100, it's going to be something like, 95 or something like that, right? No, it's going to be more like 90, sorry. The 1.96 is almost 2, so these almost cancel, right? And 9 squared is 81. So, it's going to be maybe not 90, 84, something like that. So we would suggest a few more to get a little more accuracy. It says, suppose you'd contacted 400 parents, of whom 250 responded. And some of the parents lived together in the same household. You interviewed both parents. How's that going to affect anything about your interval? Do you think this is a sensitive question at all? Physical punishment,
Not independent.
If they're in the same household, it might not be independent. So maybe the standard error, p times 1 minus p over n, might not be all that accurate. So you might, pretending that parents are independent might make it too wide, too narrow, right? You're pretending you really have 250 independent observations, but you don't. So you're kind of getting some duplicate information, perhaps. There could also be some bias, right? If the parents who don't respond were more likely to hit their kids, or vice versa, then the interval might really be shifted. It might be shifted off from the truth. So there might be a little bit of bias. The other couple of problems that are on there, there's a couple groups, 15 students who did a training program, and they're thinking about understanding animals, and they get a score, and 20 students who did not, and a difference. So you could do a confidence interval for the difference there. Would a larger sample size help? Do you reject a null hypothesis or not? Kind of another, sample size affects standard error, so it makes the sample distribution more narrow. So if the differences remained that big, then more evidence would make it. What assumptions? T, normality, simple limit theorem. And then this one is a comparing two proportions. So there are some examples of things that are on there. But any further questions or anything you want to go over from this? You know, one suggestion is to kind of write out your pages of notes, you know, front and back of a piece of paper, include the formulas you think you need, go over, you know, what we've done in class, what you need, you have all the formulas you need for this review sheet, go over the homework assignments, see if you have those, you know, what sentences you have to write to explain things, you can think about having those. And then, you know, put everything aside except for just that, and go back and try to answer the problems, and if you can figure out what to put in and tell what type of problem it is, then, you know, that's good practice. Okay. All right then, so if you have individual questions, I'll hang around. If anybody didn't get a copy of this tea table that you want to take, huh? You didn't want to take it? You like that one? Again, I'll put a copy
Maybe they'll have
on
a
the
laminated
exam.
copy of that.
Don't need to bring it. Yeah, see you. Okay.
Thank you.
Yeah. Postering.
Yeah, Common Ground is doing a dance.
Oh, okay.
Next
Good.
week, so gotta put up posters.
Cool.
Thank you.
Yep.